Hello, everyone. We're doing a practice problem podcast. So we're going to call this one podcast 3.4, and we're going to do sample problems from packet 3.2. One thing I want to make sure that you all hear right now is that I am putting discussion boards up, and they are on and open right now. They will be checked from time to time tonight by me, but if you find yourself knowing some of the answers, go ahead and answer those for people. Be part of the discussion tonight. Before we jump into any problems, I want to take a look at page 2, where we're doing the PhET simulator, and I'm asking that you determine how force and mass and motion are related using the PhET simulator. And so I'm not going to pull up the PhET sim, but I would like for you to consider that anytime you do something like this, you're going to have one independent variable and one dependent variable, and anything else outside of that is a constant. So if you think about how that PhET simulator works, you get to manipulate the mass, you get to manipulate the force, and then you figure out what the motion is. The motion is read to you, and that motion is going to be in terms of acceleration. So that is a very good dependent variable. And you also have, you can plug in any of these that you want. You can plug in the mass and select like the sleeping dog or the file cabinet or the refrigerator, or you can just take one of those objects and apply a force to it and apply different forces to it. However you do that is really up to you. So I could, put the mass here, and I might say dog, or let's see, or I think it's a file cabinet. And those have different masses, and then you can find out what the acceleration is if the force stays constant. Okay, or you can put the force over here, and you can select like maybe 1,000 newtons and 2,000 newtons and 3,000 newtons, and just make sure that your mass is constant. Either way, you can complete this. But remember, you're always finding your acceleration. That's your motion. So I just cut out page 3 because we've already done that, and so I want to just go straight into number 7 here. And we're going to draw some diagrams. And one of the things that we've got to make sure that we're doing is we're understanding, well, two things. Number one, every object has forces applied to it. So each one of these boxes has force of gravity and has the normal force. But those are equal and opposite because the box isn't floating or it's not sinking into the ground. So if they're equal and opposite, we can not worry about them. But in this question, it talks about two different forces, a 30 Newton force and a 20 Newton force. Now, forces have magnitude, and that's 30, and that's the 20, but they also have direction. So, as we said before, they are vectors. And that just means they have direction. So, if I push on this box and one of the forces is 20 newtons, and one of the forces is 30 newtons, I'm going to have a net force. And any force that is in the same direction can be added together. So my net force, let me just say F sub n E t equals 50 newtons. But wait a second, I'm not quite finished yet. I've got to include an arrow. So we can put that arrow below it. Otherwise, we can put it on top. Okay, you don't actually have to put both like I just did there. So let's actually get this one down out of the way. Okay, so 50 newtons in that direction. The second case, we have them working in opposite directions. So we have 20 newtons here, and we have 30 newtons in this direction. So this case, they're going to work opposite of each other, so we can subtract them. So this is going to be 10 newtons in this direction. Make sure I put my label on there. So that's our net force. Let's do the same thing with number 8. Let's draw a car, and let's see here, with really small tires. All right, so gotta make it bigger than that. That's ridiculous. Okay, so we have 4 forces working in 2 dimensions here, and I'm gonna have to expand this a little bit. So this is, let's make this a little thicker. So we have force of normal. We also have in the other direction force of gravity. Okay. Then we also have the action force. In this case, it's the car moving. It's the engine driving it. So we'll just call that F sub A. And then all the friction forces combined. So air resistance, rolling friction, there's probably a little sliding friction when the car turns. All of those forces are the frictional forces. Now, in this case, the family car is moving along the highway at a constant velocity. Constant velocity means no acceleration, and no acceleration means all of the forces are balancing out so that there is no acceleration. Okay, forces, any unbalanced forces means you're going to have a change in velocity. So all the forces are balanced, which means the normal force and the gravitational force are equal, and we know that because the car is not floating away. But then the force of friction and the force of acceleration are also equal, and they're opposite, equal and opposite. So the net force is 0. So why are we running the engine? Well, there has to be an action force in order to equal out the frictional force. So because friction is there, we have to run the engine to have an action force. That's why it's good to have less friction when you're driving down the freeway. Then you have to apply less force, and that means save money on gas. Okay, here's another. We're actually going to borrow the box from above. We'll take this box. Oops, gotta get that off. No, not that. Well, we'll just make a new box, and we want to talk about the horizontal force that is acting upon the box. We'll make it horizontal in that direction. We're going to give it a value of 100 newtons. So there are 3 other forces acting along that box, or on that box, and one of them is the normal force. Another one is the gravitational force. And then, of course, we have good old friction. So the frictional force. That's working opposite of the action force, which we can write in red. So let's review this question again. The horizontal force of 100 newtons is required to push a box across the floor at a constant velocity. You see this pop up a lot. So same thing as in number 8. Okay, we saw that when there's a constant velocity, the net forces are all 0. The forces are balanced. So net forces are balanced. So the net, if it's a constant velocity, that means, and I'll keep explaining it. Constant velocity means no acceleration. If there's no acceleration, that box is moving. Just like the law of inertia says, it's going to keep moving at the same velocity. Okay? So even though there's force, the normal force, the gravitational force, the frictional force, this box is moving right along, constant velocity. There's no acceleration, so the net forces are balanced and they are 0. And then what is the amount of force of friction acting on the box? Well, if these net forces are 0, that means the force of friction must be equal and opposite to 100 newtons in the other direction. So let's write that in green here. This is going to be 100 newtons, but it's going to be in the opposite direction. All right, let's go down to number 11. Number 11 asks for force. The force needed to push an object that has a mass of 10 kilograms and you're accelerating it at 3 meters per second. Well, we have an equation for that. It's force equals mass times acceleration. And we have both of those, and we're looking for the force. So let's set this up, and we're going to put the destination down. And usually, well, we're always going to answer in newtons, but in this case, we want to end up with kilograms times meters over seconds squared, which is, if you haven't committed this to memory yet, you should. That equals 1 Newton. So we want to line up all of our units so that we can come up with this at the very end. So I have my mass of 10 kilograms. Whoops, that looks like a 16. Let's try that again. (10 kilograms) times 3 meters divided by seconds squared. Okay, so the kilograms, the meters, the seconds squared all can come over to here where they show up. Meters right there, seconds squared right there, and then we can just multiply 10 times 3 to get 30. And our final answer, then we'll convert what we've got right here into newtons, so it's going to be 30 newtons. Now, I'm going to tell you number 10 is a lot like number 11. The only difference is you are asking for the net force. Well, that's similar. The difference is, instead of giving you acceleration, because they give you mass here, you have to actually figure out how to get the acceleration. And the way you do that is use this equation here. So I'll let you guys do that on your own, and you can use number 11 as a guide. Alright, number 13 and 14 have to do with falling things, an object falling through the air. And the question is, does its acceleration increase, decrease, or remain constant? So let's draw an object, and then we'll put the forces upon it. Oh, let's see here. I'm drawing a Christmas tree ornament, I think. It's kind of hard to tell with my drawing. But that Christmas tree ornament is going to fall through the air, and the force acting upon that Christmas tree ornament is force of gravity. Piece of cake, right? Now, we know the force of gravity is going to equal, using Newton's second law, the mass of the object times gravity, 9.8 meters per second squared. Let's write that down. Gravity equals 9.8 meters per second squared. Whoops. You up there? Okay. There. You get the point. Now, the other force acting upon this object, this Christmas tree ornament, is going to be air resistance. So we'll make that F sub r. Now that increases, first of all, it starts off and it's very small, but as the speed of the object increases, okay, that air resistance then also increases. Okay, it's like the molecules of air are pushing back upon this ornament. And so as this force gets bigger and bigger and bigger, greater and greater and greater, what will happen to the acceleration? Well, it starts off at 9.8 meters per second squared. But as forces keep acting upon it, that acceleration does decrease. Okay? It gets smaller and smaller and smaller until these two forces are equal and opposite. Now, if this is just falling off of a Christmas tree, that's never going to happen. And you're going to have little glass shards all over the place. But if it was falling out of an airplane, then the resistance force and the gravitational force would be equal and opposite. Now let's jump into the next question and kind of use the same thinking. An object with a mass of 30 kilograms is falling and experiences a force due to the air resistance of 50 newtons. So we actually know what this resistance force is going to be. Let's draw another object. We're going to make this object let's see, this is going to be a slightly it's for 30 kilograms, it's a big cantaloupe. Kind of a cantaloupe. All right, so we're going to draw the force of gravity. And we know that this force is going to be the mass times gravity. So the same thing as that we have over there, or up there, mass and gravity. We know that the force of air resistance is going to be working opposite, and we actually know the value for this right now. It's 50 newtons, right? Because we just wrote that in. But we can also figure out what the gravitational force is based on the fact that we know what G is and we know what mass is. Okay, and so by knowing what the mass is, we're going to put down 30 kilograms times 9.8, and I'm going to have to really write this in small, meters per second squared. That's a meter, okay? So force of gravity is 294 newtons. Okay. So I'm going to start writing down here a little bit. We have one force that is pushing up on the cantaloupe, that is 50 newtons, and we have one force pushing down, that's 294 newtons. So what's the net force on the cantaloupe? Well, it's going to be 50. Take away 50 from 294, and it's going to be going down. So the net force is equal to 244 newtons going down. So let's take this and bring it up to here, and we want to calculate the acceleration of the object. It's 244 newtons, and we know that the mass is 30 kilograms. So using force is equal to mass times acceleration, or we've got the force and we've got the mass, and so we all have to do is solve for the acceleration. Now I'll just set this up right here. Our destination, I'm going to use a different color to kind of separate. So we're going to finish up with meters per second squared. And that means we have to cancel out some units. So I'm going to make sure that my 244 is written in kilograms times meters over second squared. And I now need to cancel out my kilograms. And I'm kind of running out of space here. But I'm going to put 1 over 30 kilograms here. Same as dividing by mass. I'm going to cancel out those kilograms. And my final answer is going to be 244 over 30 meters per second squared, which if I do the math, 244 divided by 30, I'm talking to my calculator right now, but it's 8.1 meters per second squared. Let's circle that, or square it, box it in. Whew! Lots of work there. I hope you were able to follow through. Alright, I know how some of you are a little bit more visual, and that last slide was a little bit messy, so let me just kind of go through this when I redrew it for you. Here's the force of gravity. Turns out to be 294 newtons, and it's a downward force. Here's the force of air resistance. It's 50 newtons. We knew that from right here, and that's going up. So you subtract the two to get the net force. It's 244 newtons. Drag that down here. We know that that's the force, and we also know that the mass didn't change. It's still 30 kilograms. And so we're looking for the acceleration. We know the units have to be meters per second. And so we set it up with 244 kilograms times meters divided by second squared, and then we divide it by 30 kilograms, where I can just write it down as 1 over 30 kg and cancel those out. So I'm left with meters per second. 244 divided by 30, 8.1, and I'm done. All right, let's finish up here. Number 18. Which has the greater momentum, a heavy truck at rest or a moving skateboard? Well, a moving skateboard has velocity, but a heavy truck at rest, velocity is equal to 0. It's supposed to be meters per second. And so you put anything into this equation, multiply it by 0, you're going to get 0. So the greater momentum goes to the moving skateboard, who has a little bit of mass and a little bit of velocity, but still more momentum. So we can determine the momentum of the following objects using the equation mv equals p. So baseball with a mass of 150 grams and a velocity of 15 meters per second, we would have to multiply 150 grams times 1 kilogram over 1,000 grams to get 0.15 kilograms. 0.15 kilograms times 15 meters per second. I'm running out of space, but it's going to be 2.25 kilograms times meters divided by seconds. Alright, and the rest of these will do the same way. Just make sure your units line up and you'll be set. Have a good night. Make sure you are wrapping up packet 3.2 today.